Okay, well, welcome everyone. We're still at Connected Data London's meetup, our first event for the year, dedicated to graph machine learning and data science. And it's the second talk of the evening or morning, depending on where you are. Either way, the one thing in certain is that we have Bob van Lout with us tonight from Semi Technologies, founder of Semi Technologies, and he's going to be talking to us about Weaviate, the vector search engine promoted and created by Semi Technologies. I should also mention here that Semi Technologies is the sponsor for today's event, so big thanks, and hope you enjoy. So the floor is yours.
Fantastic. Thank you so much, George. I'm looking forward to presenting to everybody here. So first of all, a quick introduction. So my name is Bob van Lout. I'm based out of Amsterdam, and I'm one of the two co-founders of Semi Technologies. And we are indeed responsible for Weaviate, for the Weaviate Vector Search Engine. What I'm going to do today is I'm gonna tell a little bit about the vector search, like what is it, what are vectors, how do you deal with these things, and what problems do they solve. Then I'll slowly move up in the stack, if you will, to talk a little bit more about the problems that we can solve with a vector search engine. And I'm going to talk a little bit also about use cases. And of course, I should not forget to mention that I'm going to give you a demo, of course, as well, so that you can see it in action. So that's my goal for today. So we start low level, and then we slowly work our way up. Sometimes people want to, know even more, deeper level stuff. And then I would like to also invite you at the end to go to our website, and you can read all about it. You can go drill into the nitty-gritty details, or you can be more, if you want to be more concrete about how companies use Weaviate, you can all find that also on our website. So now I just introduced what we're going to talk about. So first about Weaviate. So Weaviate has a focus on it's called the AI-based vector search engine, and it has to do with that machine learning models. They output vectors. And one of the cool things that you can do with vectors, or actually one of the problems that we have in data sets, is that if we store data in databases or in data warehouses or wherever we store them, then the way to retrieve them is that all we need to know exactly where they are located. So for example, we need to have a unique identifier, or we need to have something else to retrieve them on, or we need to have a keyword that we search for, and we need to know the exact keyword. So for example, I like to give the example that if you have a data object that says the Eiffel Tower in Paris, then if you store that in a database or in a search engine, the only way that you really can find it is by searching for Eiffel, for Tower, or for Paris. But thanks to these machine learning models and a vector search engine like Weaviate, you can also retrieve these documents, for example, by searching for landmarks in Paris. And I'm going to talk a little bit about how that works. So if you go like vectors, I never heard of vectors, I never seen vectors, I'm just going to give you just a quick overview, like what they are and what they do. And I will also talk about why I believe that this is the future of search and how we store our data. So we always like to internally take the example of wine. My colleague Laura wrote a very nice article or a blog post about outlining how she's actually working with a wine data set in Weaviate. And so let's say that we have a data object, right, that we see here, and this is a JSON object. But even if you are if you can't read the JSON, I think this speaks for itself, right? So this is a data object. And then we see a wine, which is a Chardonnay, and somewhere in the description it says that it's good with fish. So in a traditional search engine, if we want to, or in a traditional database, if we want to retrieve this and we search for wine for seafood, then no, it will not find the wine, or it will not find any products, or for that matter, any data objects. Because as you can see, that combination, wine for seafood, or even the word seafood or the word wine, is not in the data set. So that's why you can't find it. So you need to somehow do something to retrieve that document from the database. However, if you look at Weaviate and you search with wine for seafood, you will actually find this data object, because thanks to the models, Weaviate knows that Chardonnay is a form of wine and fish is a type of seafood. So that's how you can find better results in your data set. And it's even estimated that 80% of data that we deal with on a day-to-day basis is actually unstructured data. So this, and what we mean with unstructured data is that there's not a clear structure that the machine can work with. So let's say, for example, if you would work with a bank transaction, you could say the amount of the transaction or the timestamp of the transaction is very structured, but the description of the transaction is a form of unstructured data. And often in unstructured data, we not only look at text, but we also look at images or audio or video and those kind of things. Something we will say about, we'll look at as well. So I should say, always like to take Google search as an example, because sometimes people, they ask us, they say like, okay, sounds very fancy, these vector search engines, but what is it? Who uses a vector search engine? Now, and the answer is very simple. A famous vector search engine is Google search, right? So if you search on Google, like what color wine is Chardonnay, then the query is relatively abstract. The question is like, how did Weaviate find this node in the knowledge graph? We're going to talk about the graph part later, but how did they find this node? And then, of course, the big question is, how can you do that with your own data, and how can you do it so fast? And that was the core. Those were the core two questions that we wanted to solve with Weaviate, and the problems that we wanted to solve. We wanted to make similar technology available for businesses or any other type of user, that they could create these kind of solutions with their own data. Now, of course, if we look at Google search, we have a search bar where you get search results. And with these kinds of search engines, of course, we don't know how people want to use them. So what you will see also with the use case, you will see that people use them in different ways than only working with a search bar. So for that reason, Weaviate ends at the API level. The demo that I'm going to give you is also until the API level. But the big upside of that, of course, is that you can integrate that API into any application that you have. So again, so this is the question I want to ask. How can we do that in an easy, fast, secure, and scalable way? And I addressed the fast and the scalable, but for easy and secure, when it comes to easy, so we strongly believe also in developer UX, and so that we want to make it easy for people to use these kind of models. So what you will see also in a bit, how we hope at least how simple it is to run Weaviate and work with these models, even if you're maybe not that knowledgeable about machine learning. And what we mean with secure in this context is that Weaviate runs everywhere. So you can run it, we have a SaaS offering, but you can also run it on your own infrastructure. So let's look a little bit more at the definition of Weaviate. So Weaviate is cloud native. So what we mean with that, it's that with cloud native, we don't mean that it is only SaaS, but we mean it's ready for the cloud. So you can run it everywhere on the public cloud, but we even already see users and customers using it on their private clouds, but that they use, for example, Kubernetes and those kind of things. The fact that Weaviate is modular is, we believe, very important, because different use cases need different types of vectorization. Sometimes you work with text, sometimes you work with images, sometimes you work with a combination of those. So therefore, it's modular. It's real time, or dare I say near real time. So we try to present the results to you as fast as possible. So the demo that you will see in a bit, that's actually running in the US, and I'm talking to you from Amsterdam. So it needs to travel to the US, do the calculations, and send it back. But you will see that it's relatively fast. And it's a vector search engine. So it really focuses on storing these vectors and searching through these vectors. And what's important to mention about Weaviate is that it not only focuses on these vectors, but Weaviate is a true a database with create, write, update, and delete functionality. allowing you to also store your data objects with your vectors. And what we mean with scaling your machine learning models is the fact that if you vectorize and store data in Weaviate, you can do that on super large data sets. So a little bit about what vectors are for those who do not know. So the easiest way to think about vectors, if you look at the image on the right-hand side, if you look, for example, at text vectors, is that it functions like a space. So a vector is you could imagine it to being coordinates to place something into space. Often many more coordinates than just 3, but for this example, we're just going to work with, well, 3-ish in this case. But the thing is, what the machine learning model does is that it tries to organize that data closely to how it relates to each other. So for example, if you see here apple and banana, they're somehow related to each other, and beer and wine are somehow related to each other. But for example, apple and meat, well, then they might not be related to each other, or wine and fish might be more closely related. However, the model is trained, that is how the data is structured. So what we can do, so we have multiple types of models with Weaviate, but we have, for example, one module that we mostly use for classification that is trained with something called fast text, which organizes all these individual words. And now what happens is that the moment that you store a data object, so as you see here, for example, the Covey Run 2005 Chardonnay, the model tries to determine a new vector position for this data object. And what you can see here in green, this is how it places it in the vector space. So now if we start to search for this data object, we don't need to make an exact match, but we look for things that are in the vicinity. So as you see here, that with this orange bulb, and we search for wine that fits with a seafood dish, it does not literally have to find these words or these concepts. It can just find it in the vicinity of the neighborhood. And this is in a nutshell how these models work. So regardless if you talk about images, and there are also, of course, different types of modules, and under the hood, they work differently and they vectorize differently. But the point that I find important to get across is that you know that what these models do different than traditional data sources is that they try to organize the data in a space. So what we do with Weaviate is that we say, well, we have the pre-trained machine learning models that you can have, for example, NLP. You can add your own data, which or automatically gets vectorized by a module, or if you're a data scientist and you want to do your own vectorization and store it, that's also possible. You can add your own data, and now you can start searching it, and that results in Weaviate being the search engine that we're talking about today. So we're now going one step higher. So now we know how a vector search engine works, but now, of course, the big question is, so what can you do with it, and what kind of functionalities does it have? Now, and what we see in use cases with Weaviate is that the core 2 functionalities are around search and discovery. So that means that it becomes easier to, for example, find products, find line items, find emails, find tickets, you name it, anything that's a data object, but also classification that comes out of the box with Weaviate. So what the use case we will look at a bit has a little bit of a combination of both. And what we mean with classification is that the graph-like model that Weaviate has, you can also automatically make relations in the graph model. Then about the core features, just as a recapitulation. So those are the modules, and we keep just extending modules, throwing modules out there. These modules are for natural language processing cases. They are for image recognition. We're even looking at modules related to a gene vectorization. Everything that you can do in the vector search engines, we're creating modules for. This means that Weaviate supports any media type. So the demo I'm going to show you is really focusing on text, but this could also be images or videos and what have you. Weaviate has a graph-like data model. So what we believe that it's easier for the end user to actually be able to store that data in a graph-like fashion and then search through the nodes in the graph. That's something that you also will see from my demo. and we're focusing on speed and scalability. So the one of the goals that we have is, as we always say internally, is like the inspiration came from Google Search. So we want to be able to grow to the sizes of Google Search, and we want to be able to do that for any data set that you have, for example, in your organization. Brings me to the demo. So if I go to the demo, I first want to quickly show you how you can try this out yourself, and then from there out, I'll weave in the demo. So on our website, we have a developer section. So there you can click on Weaviate, and then for the technology-minded people in the audience, you can see on the left-hand side, you can see the whole documentation, you can see tutorials and those kind of things. But what is interesting is that the way to query to your data set, we use GraphQL. And GraphQL is originated with Facebook. It's now part of the Linux Foundation, and it's a way of writing graph queries that's currently being adopted by a lot of people. And one of the upsides that comes with that is that there are many libraries available that you can adopt also to use on top of Weaviate. But not in the least important to mention is that we did some research also with developers, and they said that they very much like GraphQL because it's easy to understand, it's easy to read. So the demo that I'm going to give you is in GraphQL, but I'll promise you, if you don't know how to write it, you will be able to read it and to understand it. So what you're looking at right now is something that we call the console, and the console within Weaviate is a way to, if you have a Weaviate, you can easily search through your data. And one of the things that you can do is that you can type in queries based on your data set. And the demo data set that we have available, which you can use as well through the documentation, contains news articles and news publications. So let me increase the size a little bit. George, please let me know if it's too small, then I'll increase the size.
I think it's okay. Yeah.
Okay, let me get one more. Sorry. So so what we say within Weaviate, we can select, well, we want to get something out, and now we'll look at the class of the graph structure that we want to get out. So we say like, well, for example, we want to get the articles out. And the articles, they have properties. So for example, an article has a title. So this very simple query tells Weaviate, okay, show me all the articles and show me their titles. Now, nothing fancy is happening here right now. We're just retrieving the articles and the titles from the data set. If we say also show me the summary of that article, then we see these articles again, but then with the summaries included. Now, where it becomes interesting is we're gonna ask the machine learning model to show its magic, if you will. So one of the things that we can do is that we can say, well, I want to have one of the features that Weaviate has is something that we call near text, and we can search for concepts. So let's say that we say, well, let's look for housing prices and show me the first 5 results. It's the same query, but now Weaviate will organize the data based on the concepts of housing prices. Now, if I run this query, you see that the titles that it sends back, fair enough, here it says house prices, so very closely related. But the second one is about 5 of the world's best suburban homes for sale. So you see that both the word housing and prices is not in there, but it's definitely related to each other. And that comes because it does it searches for these vicinities, in the vicinity of these data objects. And one of the things that we can also say with Weaviate is that we say, well, Weaviate, tell me how certain are you of these results. So if I now run this query again, you see the certainty, and for the techies in the audience, the certainty is related to the distance from the query to the data object. And here you can see how Weaviate organizes this. So one of the things that we could do is that we can say, well, now let's take the limit away, but we say, well, I want you to be at least 70% certain for this query. So now run this query again, and you see that these 2 are returned. We even can go a step deeper. So we could say like, well, for example, we want to search for housing prices in, let's see, yeah. So if we say like, show me the housing price in Scandinavia, and we run this query, something interesting happens. So we see that it returns one result above 70%, but as you can see in the title, there's nothing here related to Scandinavia. So let's dig it a little deeper. Let's look at the summary of the article. And let's see what's in the summary of the article. So we see research, air quality monitoring, etc., better welfare organizations. Let's see if we see something. And here we see that it found a relation with the Finnish year. And that is why it returned that result for housing prices in Scandinavia. But one of the things that we can do with Weaviate is that we can go even a step deeper. So we can not only find these nodes in the graph, we can even search inside the nodes. So let's do that as well. Let's say I'm gonna remove the summary, and I'm gonna say, well, we want to do some question answering. So I'd say ask based on my data set. I have a question. And the question that I want to ask is, what COVID vaccine is available? So this, of course, we have news articles. So this is probably something about COVID in here. We can say that we want to find the answer in the summary of the article. And then last but not least, we want to, of course, see the result as well. So that we say answer, of course. Oh, apologies. Answer. And then we want to see the result. So what this query does is like, it says like, try to find the right node in the graph that is about, that should contain the answer, what COVID vaccine is available, and then try to find in that node in the graph, in the summary, that answer. And then, of course, we want to just see one result. So now, if I fire off this question, it's searching through the graph, and it says, well, I find the Pfizer COVID-19 as a result of the vaccine that's available. Now, what the cool thing is that we can now also introduce the graph relations. So we can ask Weaviate, well, in which publication was this published? So we can say on publication, and we say, show me the name. So the exact same query, but now we say in which publication was this answer found. So now if we run that query again, it says we found that answer in The Economist. But we can even go a step deeper, and we can say like, well, what COVID vaccine is available? And then we say, besides, for example, the Pfizer result. So the exact same query, but we even narrowed the question down a little bit further. So now if you run this query again, we see that it returns AstraZeneca, and that's also coming from The Economist. Now, this is a combination how you can see how we can search through the graph, even go as far as question answering, find the nodes in the graph, and also make relations like, for example, the publications with The Economist. And this not even goes for like, these are like individual words or smaller words, but we can even get like back longer results. So we can say, for example, what to do? You have a holiday from the let's see, from the Royal. Oh, and I made a typo. A holiday. So what to do when you have a holiday from the Royal Ballet? So let me run this query. And then the answer is like, you take on a guest appearance with other companies. And that was published in the International New York Times. And now what we can even do, one step deeper, we can say, well, show the summary where you found this answer, but also show me the start position and the end position of this answer. So now if I run this query again, you can see that the start position is at 304 characters in the summary of this article. So why did you want to go when you have a holiday? Here you go. So it starts. This is where it starts. So this is how you see how you can make these combinations. And there's one more feature that I want to show you before I continue. And because it's a graph, we can also take another perspective of looking at this graph, right? So we now looked at the articles, but now let's look at the publications and say I want to see the names of these publications. So I run this query, and here you see the the names of the publications and that have articles in this data set. Now, there's something that I want to highlight from this data set. As you can see, and this is something you see often also with data harmonization and data management, you see here we have the New York Times company, but here we have the International New York Times. And what we know is that these newspapers, they're stored as different data objects, but they represent the same thing. And even here we can do something with Weaviate, so we can ask Weaviate to say, well, we want you to merge, where are you? Let's see what that query is again. Oh yeah, of course, apologies. We want you to group the data together. The type that we want to do is we want to merge them together, and now we need to give them Weaviate a force to merge. That basically means you remember that space. So how big in that space when you cluster everything together? So we're going to say, well, just 10% merge together. And now if I run this query again, what you will see is that it grouped the New York Times company, the New York Times, and the International New York Times together because it knows it's the same thing. We can also say that instead of merge, we have the closest. So then we ask Weaviate, well, just combine them together, but just show us what you think is the best result for this to represent this data object. And then it says, well, I believe that's the New York Times company. And now the powerful thing with Weaviate is that we can even say, like, because it's a graph, we can say has articles, we can say on article, and then we should say title of the article. And so Weaviate still is able to make these graph connections, even if we've asked the machine learning model to group these together. So if I now run this query will take a little bit longer because, oh, wow, faster than I expected. But it got out of all the articles that it has stored, and it even now combined from all these different New York Times publications, everything together. We have way more functions, but the time doesn't allow for that. So I would like to invite you to look at the website as well. Do I have a few more minutes, George, or do I need to wrap up?
Just a few. So basically you have a choice. Do you want to continue with the last part of the presentation, or do you want to take some questions? Because there's already some questions, and I think we have something like, 7 minutes left.
Then please allow me 2 more minutes to quickly go over an example case, and then I would love to take questions.
Yeah.
One of the example cases, because we didn't talk about how this is used, right? So how do companies use this in production? And on our website, you can see a great video of somebody from Metro. His name is Sebastian Hilscher. So you can find it on our website, and he talks about the case that they have. And the use case that they're using Weaviate for is that they want to find new bars, restaurants, and hotels in Europe. But the difficulty that he had was that the name of a bar, hotel, or restaurant might be different from the way that they stored these names in, for example, from invoices in their internal systems. So what they've done is that they created their own application, a CRM application, and they have one Weaviate. They load the Weaviate with data from the data warehouse, and they load the Weaviate with on a daily basis with OpenStreetMaps data, and Weaviate automatically tries to make relations, just like I just showed you, between bars, hotels, and restaurants that are in their data set and that are coming from OpenStreetMaps. And the power in here sits in the fact that if Weaviate can't make a relation, they know it's a new potential customer. It brings me to the last point. If you recognize these kinds of business problems and you think that we could help you, then we often see that we can help with data harmonization. So if you have different databases or data warehouse or ERP systems and you want to harmonize the data together, Weaviate is a great choice to solve that problem. You can use Weaviate to predict data. So for example, if you have use cases in where you want to know what kind of data objects you need to add related to other data objects. So for example, if you have that document about the Eiffel Tower in Paris, then Weaviate could make a relation that's a landmark, and now you can store that data as well. And then of course we have the classification cases where you can say like, or by searching through the data set, or by automatically have Weaviate make these relations through the classifications functionality. So, well, quickly, we have all these integrations available. We have a SaaS solution available. We have the console available for as a GUI. But last but not least, then please reach out to me if you have any questions or if we can help. So thank you for listening, and I would love to take your answer your questions. Thank you.
Okay, so I got a couple of easy ones. One is there's somebody asking whether Weaviate is open source. I can make your life easier. Yes, it is. It's on GitHub. It's actually trending on GitHub, I saw these days. So yes, it's open source.
Yeah.
Another one, there's somebody asking whether the slides are going to be available. I suppose yes.
Sure. Yeah.
Mm-hmm. Okay, and then I guess we have like time for one actually really meaningful in-depth question. So people are asking whether Weaviate is built with embeddings on a knowledge graph.
So the if I understand the question correctly, so Weaviate itself has a graph data model. So as you've seen, you have these individual nodes in the graph with traditional graph relations. But every node in the graph is vectorized. So that means that you can find these nodes in the graph by doing fuzzy searches, as I demoed just to you. So you could argue that that's a form of a knowledge graph. Don't know if this answers the question, but that's how I would answer it.
Mm-hmm. Okay. Okay, so we have time for another one. So Parrot is asking whether you can adjust the strength of relationships based on user behavior, as well as semantic distance.
A great question. So the answer is yes. We even have use cases where people have users in the graph. So example, think about an e-commerce example. So you have a bunch of products floating around in the vector space connected in the graph-like fashion. Now you can add a user also as a representation in the graph. And if somebody always searches for like wine and cheese, then you know that this user will float around somewhere around wine and cheese if you push them in that direction. So that's definitely something that you can do.
Mm-hmm. There's actually an add-on to that question. From Samuel, it's a kind of a comment. He says he doesn't think it would be possible to calculate semantic distance without an ontology or taxonomy controlling the words. But I think you're not using one actually.
That is correct. So and this is actually a really good question. So what we of course saw from the semantic web and traditional ontologies, of which I'm of course also a big fan, needless to say. The question was like, how are we gonna solve this problem of things being ambiguous? What if we can't agree on the ontologies? And that was one of the core ideas, was saying like, what if we just don't have to agree on them? What if we can just say like, we just create a simple RDF-like class property structure? And so you can also create a schema in Weaviate that does that. But if you want to search and retrieve the data from Weaviate, you can use any terminology that you want. So if I have a graph node that has the class business and the name, I don't know, semi-technologies, I can also find that node by searching for a company with the identifier semi-technologies. The semantics are different, but the machine learning model knows that you probably mean the same node that you wanna capture. So we try to solve this problem by completely relying on these machine learning models, and I have to say, so far so good, and I would highly recommend that you give it a try because maybe you like it as well.
Mm-hmm. Okay, and final one, and let's wrap up with this one. There's a question of whether a node is a word or a piece of text, and then what are the edges in the graph? So
another great question. So you can manually set the edges like in a traditional way. So what you've seen in my demo, for example, we knew that an article was coming from a publication. So there's an actual graph relation between, for example, New York Times and the article. So that was why we could make that direct relation. But then the only thing is we use the fuzzy matching or to find the article or to find the publication. If you are knowledgeable about these RDF-like structures, you will recognize that immediately if you look at the schema in Weaviate. But the powerful thing that we hope to add to that is that that node is not just a dumb node, just floating around in a dimensionless space. It actually, the dimensions where the nodes are positioned in the space, they have a function as well.
Okay, great. Great, Bob. You actually got to answer all questions. I hope people will have additional ones and they can join us in the community hour for that. For now, thanks again. We're closing this room and moving quickly to the next presentation in about 3 minutes. So see you there.
Thank you very much. Bye-bye. Thanks for listening. Cheers.
Bye-bye.